talk about the definitions of bonding and how to really understand what each bond is, because if we understand the definition, or if we understand the nature of the bond, then it's a lot easier to identify to predict the properties and to really understand why there is a difference in melting, boiling point, structure, and so on. So if we talk about any type of bond, okay, or actually any type of interaction at the atomic level, we're talking about an electrostatic attraction. Electrostatic. And electrostatic means between opposite charges. So because we know that same charges would repel and opposite charges attract. So we're talking about positive and negative. This is actually the key thing, the only thing that you really need to understand. Because for each bond, there would be something positive and something negative. So for each type of bond and the force as well that we look at, we need to find what's the positive and what's the negative component, okay? So if we think about covalent, actually, no, I'll do that last because there are two different ones, but let's think about ionic. Ionic talks about ions, right? What are ions? Ions are charged atoms, which means that you can work out the definition of ionic bond. Electrostatic attraction between what? Well, it's ions, but we know that ions, they must be oppositely charged. And there we go. The ionic bond is an electrostatic attraction, and I'm going to do just a random example here, between oppositely charged ions, just to revise also the dot and cross diagram over here. Okay, but it is important to understand the nature of these electrostatic charges. Ionic, between opposite ions. Metallic, it's, well, if we want to represent the structure, we normally write it like this. Yeah, so it's useful to use our visual memory as well to remember it. We have a lot of we have this regular arrangement of the positive metal ions with delocalized electrons through the whole structure. So guess what is it? So delocalized electrons, and this is the metal ion, which means that is again an electrostatic attraction, but what is the positive and negative component? Notice that it's slightly different for each bond. Ionic, opposite ions. Metallic, well, we have the positive metal ion, and because the metal become positive, they lose electron in this sea of that is like the orbital become like just one orbital in the whole structure. So the electrons are delocalized, but again, the positive component is the positive metal ion, and the negative component are delocalized electrons. Okay, so that's the other nature of the electrostatic force. Covalent, it's a bit trickier, I would say, to work it out, but not really. But we still need, I'm going to do a new diagram. We still need to think about what are the components then of opposite charges, because again, it's just like any bond, an electrostatic attraction, but in this case is the electrons are shared. And remember that we have non-metals. So non-metals, they would form a negative ions. So it's not between ions, otherwise they would repel. But the positive and negative component in this bond is between the positive nuclei and the shared pair of electrons, which is negative. So if we want to define the covalent bond, it's an electrostatic attraction between the positive nuclei and the shared pair of electrons. Okay, so notice the three different definitions, they're all in electrostatic nature. And those are bonds, so electrostatic attractions, and they're all really strong. So both ionic, so all of the three, ionic, covalent, and metallic, they're all super strong. So all of these can exist in what is called a giant lattice, which is just a giant structure. And the giant structure could be giant covalent, metallic, or ionic. And because there are many of these strong forces of attraction, they have high melting point and boiling point, simply because those bonds of the electrostatic nature, they're really strong. And as a consequence, a lot of energy is required to break them. So here I'm answering like marking scheme style, looking at the key points. Yeah, but that's the giant lattice. Okay, and this is the case if you want to break the giant structure, because we're actually breaking the bonds. But of course, for covalent bonds, they are slightly different, because we have examples like diamond, graphite, and silicon dioxide, but there are also small molecules for covalent. And the key thing here is thinking about water. H2O. H2O is a gas, H2O is a liquid, and H2O is a solid. So you're not even touching the covalent bond when you change physical state. But that's why when we change the state of these molecules, we look at the intermolecular forces. So we know that we're not breaking the covalent bond. I think this is the easy way to remember. And intermolecular forces, think about what that means. Inter means in between, and then molecular, and that's between molecules. And molecules, what are? Well, those are small covalent ones, because all the others, they will be giant structure. And that's why I think if we understand fully the definition of all of this, we can work out the structure and the explaining the melting point and boiling point, and also not get confused with the molecules, because intermolecular, between molecules. We're talking about small molecules, okay? And this is useful because in a lot of exam questions, we have to explain why some substances have high boiling point, or compare boiling point of a giant structure compared to molecules, okay? And this would be the key points that we really need to look for.